In this video, we're going to talk more about electric charge and types of materials that we'll see when discussing charge and solving problems. This is important to building intuition for what is physically happening and why, rather than blindly using equations. So this may seem a little boring, but we won't deal with any equations, and I promise understanding what's physically happening and the whole story behind charge will help a whole lot later down the road. So first, how did we discover charge, and how do we know that there are only two kinds of charge? People noticed that rubbing together two materials could cause them to attract other objects like pieces of paper, and later we said the objects obtained a charge, and this process of rubbing an object and inducing a charge is called triboelectric charging. For example, if you were to rub a glass rod or an acrylic rod with silk, the rod or acrylic would obtain a positive charge. Another example would be rubbing Teflon and rabbit's fur, and this would leave the Teflon with a negative charge. So we know there are two types of charge because charging two objects the exact same way should lead them to carry the same type of charge if they're the same material and go through the same process. Two objects that are the same and charged the same way, they will repel each other. So this is one type of interaction that we see. But then if two objects are charged in different ways, sometimes they will attract each other depending on the types of materials. From this, we're able to deduce that there are two different types of charges because they behave in one of two ways in the presence of other charges. We have never found a third type of charge or a third type of interaction between charges. All interactions that we see can be explained by only having two charges. As for why they are called positive and negative, the naming was done by Benjamin Franklin, and it's completely arbitrary. We could have called them red and blue or something else, but positive and a negative allows us to distinguish between them mathematically with a plus or minus sign, so it's really convenient. We just have to remember the negative sign only indicates the type of charge. It doesn't indicate that there is somehow less than zero charge, whatever that might mean. There is also no particular reason why protons should be labeled positive and electrons labeled negative. If we could go back, some people would probably choose to swap the labels and switch it. And you'll see why as you learn more about electromagnetism. The good news is that it doesn't matter physically or mathematically. As long as we're consistent, our models will still explain what we see in nature. So now let's look at atoms. In an atom, we have protons and neutrons in the nucleus surrounded by electrons. And from chemistry, you've probably remembered that electrons fall into different shells or energy levels, and each shell can only have a certain amount of electrons. These electron shells like to be complete, so if an atom only has one or two electrons in its outermost shell, these electrons might be easy to strip off so that every shell in that atom is complete, is full of electrons. And if the outermost shell is only lacking one or two electrons, that atom might easily take on electrons from somewhere else in order to again complete all of its shells. So when an atom loses electrons, it becomes less negative, which is the same thing as becoming more positive. And if it gains electrons, it becomes more negative, or another way of saying less positive. The key point here is that electrons are the parts of the atom that move around and get transferred in order for the charge to change. Protons, or positive charges, don't actually move most of the time. And for us, it will pretty much be none of the time. Protons or hydrogen ions can move sometimes in chemical reactions. But in physics, when we're talking about charge moving through a material, it is primarily just electrons that are moving. Throughout physics, we will treat everything as if positive charge were moving. We can do this because positive charge moving onto one object is the same as negative charge leaving the object. For example, we define the electric field direction to be away from positive charges, which lead to the electric field lines pointing in the direction a positive charge would move if it were placed in that field. This is completely by convention, and we'll continue to define everything for positive charges in this class going forward. If we're dealing with a negative charge, we just have to remember that we need to flip our signs or change the direction to point in the opposite way that it would for a positive charge. Now we'll talk about types of materials. So some materials have loosely bound valence electrons, which are just the electrons in their outermost shell. These materials are called conductors, and a common example are metals. Their loose electrons are free to flow through the material, so we say they can easily conduct charge. Materials that do not have free or loosely bound electrons are called insulators. In case you're familiar with thermodynamics from a chemistry class or something else, if a material is a good thermal conductor, meaning it gets hot or cold really easily, like metal, it's usually also a good electrical conductor too. So this is why we use copper wiring, because the metal is a good electrical conductor, but you also know that metal will get really hot in the sun. So a good thermal conductor is a good electrical conductor most of the time. So now let's talk about a process of charging an object. An object can be charged using a process called induction, which is when an object obtains a charge without actually contacting another object. For example, if you were to bring a negatively charged object near a conductor, the electrons of the conductor will be repelled and moved to one side, leaving the closer side, the side closest to the negatively charged object, to be positive. If you wanted, you could then remove the negative charge on the conductor by connecting it to earth ground and then removing the wire. Earth ground serves as a source of many excess charges for the electrons to move toward and neutralize. And we'll talk more about grounding later. But basically, since like charges repel and opposite charges attract, you can think of charges acting in such a way that they're trying to become neutral. Since Earth has excess charges, it's an easy place to dump the excess charge from another object in order for it to neutralize. Earth is so big and can redistribute the charge that we don't ever have to worry about it holding a lot of charge in one specific location and damaging us or anything like that. So back to our conductor. It now has attained a positive charge without us actually touching the negatively charged object that we brought near it. Before we connect the wire, the conductor was negatively charged on one side and positively charged on the other side. And in this state, we say it's polarized because it has a positive pole on one end and a negative pole on the other end. We can also polarize insulators. Even though the charge isn't free to move across the entire material, the individual atoms or molecules can sometimes reorient themselves such that the positive sides of all the molecules are pointing in one direction, leaving the negative sides to point in the other direction. This has the same effect as a polarized conductor, though it might not be as strong. Something in this configuration of having a positive charge on one side and a negative charge on the other side, especially when it's close together, is often called a dipole since it has two poles, positive and negative. A single positive or negative charge could be thought of as a monopole by itself, since it exists without other charge. And then you can have other higher order poles, quadrupole, octupole, in the same way. So wrapping up, throughout electromagnetism, you should be looking for these terms. For example, a metal wire is a type of conductor. So the terms are interchangeable when you see them in a problem. You should also be thinking about what is physically happening. I like to think about how charges, specifically electrons, want to behave. Even though they don't think and have a mind of their own, you can come up with these rules by which electrons behave according to the laws of physics. And then you can just think physically or conceptually about what the electron is going to try to do based on these rules. So once you know how charges behave, much of electromagnetism is just cause and effect and figuring out how to express it mathematically. Rules of thumb like electric fields point in the direction a positive charge would go, or all charges move in such a way to lower their potential energy, something we'll talk about later, will go a long way in helping this subject make sense. So the math will agree with these statements. So it's a good way to check your work and your understanding. Okay, so hopefully this video gave you kind of an insight into what's physically going on with charges, and it's something you should keep in mind as we move forward. And so that's it for this video, and I'll see you in the next one.